The Sieve of Eratosthenes. Hi viewers, welcome. This is I Darshit Barmecha along with my teammates Velina and Aman, representing Group DAV for the given assignment under the guidance of Mr. Sunil Dhimalsa. Further, not wasting more time, I would like to hand over Velina for explaining our project on Sieve of Eratosthenes.
Thank you, Darshit, for handing it over. With this, I would like to continue further explanation of the assignment. As we can see, the topic for the assignment is the sieve of Eratosthenes. So, starting with its definition, the sieve of Eratosthenes is one of the most efficient ways to find all the prime numbers up to given limit by the user. By this, we can see that it is an algorithm to find the prime numbers. So, first of all, what is a prime number? A prime number is a natural number that has exactly two distinct natural numbers divided the number 1 and itself. We can also explain it as any number that has two multiples, that is the number 1 and the number itself. That number is called as prime number. So for example, we are taking here number 5. So as we can see, 5 has two distinct divisors, that is 1 and 5 itself. So it is a prime number. So moving forward, let us see some of the attributes. As we can see, sieve of Eratosthenes is a technique formulated by a brilliant Greek mathematician, Eratosthenes, whose efforts greatly contributed to identifying prime numbers. Eratosthenes was born in 276 BC. This method is 2200 years old, so it's been a very long time. He contributed a lot to mathematics, and the discovery of sieve was the best he had done in this field. It is a pattern or algorithm that works by eliminating numbers that do not fit in a scenario. The sieve of Eratosthenes is a 1999 sculpture by Mark D. Suvero, installed on the Stanford University campus in Stanford, California, United States. Next, we will be talking about how it works or about the algorithm. The steps are given below. So briefly explaining, first of all, we have to create a list of consecutive integers from 2 up to n. The next step will be taking 2 as the smallest prime number. So let us initialize 2 as p. Now we will be marking all the multiples of p where p should not be marked. After that, from the unmarked numbers, find the smallest number in the list which is not marked. Now that number will be the next prime number. If there is no such number, we will stop there. Otherwise, we have to repeat the same steps again. Lastly, when the algorithm terminates, the number remaining not marked in the list are all the prime numbers below n. In the last slide, we saw how we can find the prime numbers in a given list of numbers. Here we will be explaining the same thing with an example. So for this example, we took n is equal to 50. As we have to find a prime number that is less than or equal to 50, let us first create a list of table from 2 to 50. Accordingly, we can see that we have marked all the multiples of 2 up to n, that is 50. Now from the above figure, we can see all the unmarked numbers. So from there, the smallest unmarked number will be taken as the next prime number. Here that is 3. So we will be marking all the multiples of 3 again up to n, that is 50. In this figure, we can see that the next number after 3 is 4, but we all know that the 4 is a multiple of 2 and it is marked. So the next unmarked number is 5. So we will take 5 as our next prime number and mark all its multiples. After that, the next number is 6. But again, we know that 6 is a multiple of 2 and 3. So we move on to our next unmarked number, 7. The multiples may already be marked as those are also multiples of 2, 3 and 5. Likewise, we go on checking the multiples of other numbers less than 50 and mark it. Here We can see in the figure that all the multiple number have been marked in red color. So the prime number are the unmarked ones. That is 2, 3, 5 and so on up to 47 as you can see in the figure.
Now let's begin. The program is the simplest form to find a prime number up to given range. Let's say it's a basic startup that includes header file declaring variables asking user for input up to which it shows the prime numbers. As moving forward, we can see there is a nested for loop where outer loops helps us to assign range provided by the user and the inner loops determines the factors for each number on those range. Let's take an example. As we can see, the user has inputted number 15 and the output is prime number are up to 2, 3, 5, 7, 11 and 13. So the range is set by the outer loop and the prime numbers is determined the inner loop. As we know, a prime number can only have two factors, that is 1 and itself. And you can see 2, 3, 5, 7, 11 and 13 just have two factors, that is 1 and itself. And what is a program without a flowchart? So let's continue with flowchart. Starting with the flowchart, we see the number is inputted by a user. If number is less than 2, the program stops here, or else it will continue to the inner loop. We know that the outer loop is just there to set the range, and inner loop is to determine how many factors are there. Here factor is represented by count. So we see count is equals to 0. It's the initial value of the count. Now moving towards the inner loop, if the inner loop executes, it checks that if a division has a remainder 0. If it has a remainder 0, it will increment a factor, that is, it will increment count equal to 1. The process follows until it's false. And lastly, if it's false, it will count how many factors are there. Now, as we know that the prime number has only two factors. If it has two factors, it will display or it will execute a prime number, or else the process goes on up to given range. So this is it, the Sieve of Eratosthenes, and the ending of our project. Thank you all for your active participation and cooperation.